So now that we've got our covalent bonds worked out, now we're going to give a little bit more time to the ionic bonds. And so really, based on our understanding of where electrons are and stable electron configurations, we're going to take a closer look at ionic compounds. And so we know from our discussion of the periodic table that these groups had some important characteristics and some commonalities. So the first group were the alkali metals. Group 2 is the alkaline earth metals. Group 3 didn't really have a common name for us. 6 didn't really, I mean, there are names for them, but we don't use them as often, so I didn't put them in here. We had the halogens over in group 7, and we had the noble gases. In talking about the common ions formed, we can take a look at our periodic table, and we know that these having one valence electron wants to give it up and to become a common ion of +1, or commonly become the ion. So we lose one electron. Alkaline earth metals become +2 and they lose 2 electrons. These ones are going to lose 3. And you can see that when you look down the periodic table and that number that's up in the top of the box, they'll all be the same as you move down. So that common ion formed is on our periodic table. You notice it's not on the periodic table in the front cover of our textbook. I think it's a really nice resource to have. Whoops, sorry. I was talking and steered you wrong. Let's move to the noble gases. So the noble gases don't form ions. They have a stable arrangement. They don't have, a number of valence electrons per se, in that they have a full shell of valence electrons. So halogens are going to become commonly a -1 ion by gaining 1 electron, and then this group 6 is commonly going to become a -2 ion by gaining 2 electrons. And so why do certain elements give away a certain number of electrons, and why do some like to gain electrons? They're all trying to have the same electron configuration as a noble gas. And so when we talk about these metals and non-metals, the metals tend to ditch their valence electrons. They have a couple extra and are left with just those core electrons in the middle. And the non-electrons gain electrons, again, to build their valence electron up until it's full. Noble gases are already complete. They're already happy unto themselves, so they don't tend to bond with other things. So here we have an example, so how they become the ions that they are. When nonmetals share, this is exactly, the covalent bonds that we were talking about. And so we're going to keep going with these ionic bonds a little bit. Okay, let's take a look at some examples of these. So practice doing this kind of stuff with the periodic table. So it says, what ion do the following elements form? How many electrons does the total atom have when it becomes that ion? And what noble gas configuration is the result? So I like looking at the periodic table for these. So phosphorus would be number 15. And I can take a look at the periodic table, and it commonly becomes phosphorus 3 minus. And so it becomes that 3 minus by gaining 3 electrons. And so it has a total number of 18 electrons. That 15 plus the 3 is 18. And that's the noble gas configuration of argon. Let's work through another one here. So let's do B next. So strontium is number 38 on the periodic table. Its common ion formed is strontium 2+. It becomes the 2+ by losing 2 electrons, so that would give it 36 electrons, which is the number of electrons of the noble gas krypton. Tellurium is a little bit of a funny one. So if we take a look on the periodic table, there's options here. We're going to talk about the tellurium becoming tellurium 2 minus. And so it becomes 2 minus as this number 56, losing 2 electrons would give it 54. So it, sorry, gains, oh my goodness, 58. Oh my goodness, I can mess this one all up. So we gain 2 electrons. The noble gas configuration of, why am I doing this one wrong? I have to skip this one. In class, I'll get it right. In the video, I'm not going to get that one right. Okay, so aluminum, let me just double check. Hang on here. Tellurium, 2 minus, 54, and xenon. It loses 2. 2 plus? There's something wrong with that. Oh, it loses 2. Nope. Okay, I leave that one. I can't think on my feet fast enough. So aluminum commonly becomes aluminum 3 plus on the periodic table. It loses 3 electrons to gain that positive ionic charge. Normally it would have 13 electrons. That's what I hadn't written down about tellurium, and I can't find that quick enough on my feet here. So it loses 3 electrons to have 10 electrons, which is the noble gas configuration of neon. I hate when I make a mistake in the videos. I'll come back to it. Sorry about that one. I'm sure you in your clear thinking are answering that for me right now. So ionic bonding and structures of ionic compounds. So how all this fits together is kind of interesting to visualize. And so when an ionic compound forms on the atomic level, you can imagine these ions as spheres. So the cation and the anions packed together. And so the geometry of this works really well because cations tend to be small. So these little positive lithium ions here, and they nestle into the spaces between the larger anions. So generally, positive ions are small and anions are large. Another important trend is that we talked about the relative size of the radius, right? And so as we take a look at the atomic radius here, we could take a look at, they're relative to the ion. So lithium as an element is bigger than the positive ion. So it's lost an electron and it's got smaller, right? Over here, fluorine element is smaller than fluorine ion. It's gained an electron and it's larger. And so it's not just the overall size, but it's these relative size. Remember I said the negative ones, or sorry, the positive ones are small and they nestle in amongst the anions. So can you think of an explanation, a way for you to remember why cations are smaller than their parent atom and why anions are larger? If you think of this, cations and anions. So these are positive, these are negative, right? These ones are the small things, and these are the larger. Been delaying a little bit. If we can think of why. Well, the cations have lost an electron. These ones have gained an electron. So just the number of things around them allows you to see that they would be larger, right? They're gonna fill them in. Again, all of these are not important to memorize. It's that overall trend that I think is important. So let's take a look at these ones. So which of the following atoms or ions has the smallest radius? And so these ones are not commonly formed. We could talk about oxygen as an element and the common ion being a -2. So if we were to kind of compare all of these ones, this one would be the smallest. This one would be the largest based on even just looking at how many electrons are around these things. Rank the following from largest to smallest atomic radii, and we can take a look at the numbers off that table that's before. So I could rank these ones. I tried to do it just conceptually and it doesn't work. You have to actually take a look at the numbers that are the measurements of these atomic radii. And I don't know the units that these are measured in, but just even if we take a look at them to relatively rank these ones, we would go from the largest to the smallest. And so if I'm going to just change color here again, we got to go from the biggest. So that would give me, how does it work here? From largest to smallest. Oh, hang on, I'm muddled again. So largest is the smallest number. That was just my relative rating, and I couldn't look at the pictures quick enough. So 1, where am I at? 2, 3, and 4. And again, having this stuff memorized is really unrealistic. So go with the resources that you're given. Okay, so the last little bit of this is to talk about Lewis structures. And we're going to go back, and I think I've already kind of debunked the Lewis structures as being overly simplistic when we talked about chapter 11 and modern atomic theory, but they really are a useful way to kind of conceptualize this. The last topic that we'll talk about in chapter 12 is just the fact that there are 3D shapes of these, which are interesting based on bond angles and the number of valence electrons. So in chapter 11, we started out talking about Lewis structure. And so in these Lewis structure, we're going to have the symbol in the middle, and then just the number of valence electrons around. And so probably we've moved past drawing the all of the, 2 and then, up to 10, all of those ones. We're really just going to summarize it with the number of valence electrons. So in these ones, these ionic compounds we could talk about as, being drawn like this. Lewis structures are actually quite useful for covalent compounds. And so let's take a look at these and some examples of these. So here we have an example for hydrogen fluoride. That was one of those ones that was polar in nature. So we're going to figure out how many valence electrons each ones have. And so we can do that by taking a look at the periodic table, right? Hydrogen would be in that first column with 1 electron. You could also figure it out from common ion formed. Fluorine has 7 valence electrons. And so we know that there's going to be a bond between these ones as they share those electrons. We'd want to finish putting the number of valence electrons around fluorine. So here's a good question. Why don't I put 7 more valence electrons around hydrogen? The reason we don't is that hydrogen is full with the duet rule. So the first 2, remember the duet rule and the octet rule. And so watch out for some of those ones, the first few elements on the periodic table. They're complete in with the duet rule. Okay, so let's go through these examples. So we want to draw out the Lewis dot structures for the following. So fluorine. Fluorine would typically have 7 valence electrons. And so I would draw the symbol fluorine, and I would have 7 valence electrons around it. And this other fluorine, 7 valence electrons around it. So these 2 valence electrons are actually going to be shared, and that bond illustrates, or that line illustrates the bond between these. Let's do another one. So phosphorus bromide here. So we'd have phosphorus, and if I take a look at it, it has 5 valence electrons, and bromine would have 7 valence electrons. Well, I have to draw 3 of those bromines. So let's start with those 3. Whoops. So I should have 7 valence electrons around here, and 7 valence electrons around here. Sometimes it takes me almost a rough copy of these ones. You're like, oh, I put the single dot on the wrong side. And then I'd have 1 phosphorus. Now, phosphorus is supposed to have 5 valence electrons around it. So it would have 1, 2, 3, 4, 5. And so this becomes a bond as it shares those electrons. This becomes a bond as those electrons are shared. And this becomes a bond as those electrons are shared. And again, these ones, the Lewis dot structures are much better for covalent compounds, because the ionic compounds, you can draw the ions, but there's not that same sharing with this line in between. Okay, methane here. So I'd have a carbon and 4 hydrogens. In taking a look at how many valence electrons are around these, carbon would have 4 and hydrogen has 1. So I could draw my 1, or like that, right? 1 around each hydrogen. And chlorine has, or sorry, chlorine, I keep saying chlorine. Carbon has 4, and that becomes the bond here. Those ones are shared. Okay, neon. It's just done. There's no Lewis dot structure. I guess it's debatable whether you put all, 8 around or none around. I think the better answer would be to put all 8 around, and it's not going to bond with anything. So number 8 here, which of the following supports why Lewis structures are not a completely accurate way? So we've already kind of debunked the Lewis dot structures way back in chapter 7. Let's read these. So we can't say for certain where an electron is located, yet when drawing Lewis dot structures, we assume that the electrons are all right where we place them. Well, that's true, but that's not why we can use these. Okay, so in adding up the number of valence electrons for a molecule, it's possible to get an odd number, which make it impossible. That's not really what's wrong with this. So both statements 1 and 2 support why Lewis structures are not a completely accurate way to draw. That's probably the best. So this is true. We don't know for certain where they are. Remember we talked about clouds of probability in chapter 11, right? And when we talked about orbitals. And adding up, we might, have some trouble with the number of valence. There's a lot of exceptions. And Lewis structures are the most, well, no, they're not completely correct. We already know that. So both these two are true statements. The last little bit of this is really something that's fun to do with on campus. So we can take a look at molecular structure and the way that these molecules fill up space. And so generally molecules have different shapes, and these just kind of give you an overview of some of those possibilities. And like I say, it's really fun if you can build these on campus. We can use a molecule building set, so build models. And I keep looking for an online simulator for that because it's really very specific about how these molecules come together. You get a bit of a sense of it with drawing the Lewis dot structures, but we've just kind of debunked some of the Lewis dot structures. So I didn't take this chapter as far as it goes in the textbook for that reason.